I am standing beside a farmhouse in Holmes County, Ohio. It is August 14th, 2017. The temperature outside is 93 degrees. I press my palm against the south wall. The surface is hot, almost too hot to touch. But when I step through the front door, the air hits my face at 74 degrees. No compressor running, no fan humming, no thermostat on the wall. I spent 20 minutes looking for the AC unit. There was not one. This family has not paid a cooling bill since 2006. 17 summers. 17 Augusts in Ohio. And the column on their wall has never needed a repair, a filter change, or a single wire running to it. And in winter, with one simple adjustment, the same column reverses and pushes warm air inside instead. The grandfather of this family built the first version in 1947. His son improved it in 1963. And now the grandchildren know how to build it too. 3 generations, 76 years of refinement, and not $1 paid to a utility company. But the roots of this knowledge go back much further than that, passed down through generations who understood that dependence on outside systems meant vulnerability. You will not find this in any modern building manual. You will not see it on any home improvement show. And there is a reason for that, a reason that has everything to do with who profits when you stay dependent and who loses when you become self-sufficient. By the end of this video, I am going to show you exactly how this system works, what it costs to build, and a forgotten technique from a 1951 agricultural extension report that nearly everyone has missed. It works even if your home was built 40 years ago. You do not need to tear down walls. You do not need a contractor. And you can test the basic principle this weekend with materials from any hardware store. The first time I walked into one of these homes near Millersburg, I spent 20 minutes looking for the thermostat. There was not one. The house was cool, the windows were closed, and the only thing I could hear was the soft movement of air through a vent near the floor. I remember standing in that living room on an August afternoon in 2017, the temperature outside pushing into the low 90s, and feeling genuinely confused. The comfort was undeniable, but I could not identify its source. I asked the homeowner how it worked. He smiled and pointed to the south wall. There was a glass panel covering a dark column that ran from the foundation to just above the roof line. He said his grandfather built the first version in 1947, before air conditioning was something regular families could afford. His father improved it in 1963, adding better sealing around the glass and extending the column another 4 feet to increase the draft, and now his children knew how to build it too. 3 generations of accumulated knowledge, refined through direct observation, tested through harsh Ohio summers and winters alike. That conversation changed everything I thought I knew about keeping a house comfortable. It also started me on a research path that would take years and lead me through dusty agricultural archives, conversations with retired extension agents, and visits to communities across Pennsylvania, Ohio, Indiana, and Virginia, where this knowledge never died. The basic principle is so simple that it almost sounds like it cannot work, but it does. And it has worked for thousands of years in different forms across cultures that understood convection before anyone gave it that name. The ancient Persians built wind towers called badgers as early as 4,000 years ago to catch breezes and channel them into buildings. The Romans designed their villas with central atriums that created natural air circulation. Traditional architecture in hot climates from Egypt to Iran to the American Southwest incorporated passive ventilation strategies that modern builders have largely forgotten or deliberately ignored. Here's what happens inside a solar chimney. You build a vertical column on the south-facing wall of your house. The outer surface of that column is covered with glass or a clear panel. Behind the glass, you paint the inner surface flat black. When sunlight passes through the glass and hits that black surface, it heats the air trapped inside the column. Hot air rises. That is the only engine this system needs. No moving parts, no fuel consumption, no maintenance schedule, just the same physics that makes smoke rise from a fire and hot air balloons lift off the ground. As the heated air rushes upward and exits through a vent at the top of the column, it creates negative pressure inside the house. That negative pressure pulls cooler air in through vents positioned low on the opposite side of the building, usually the north wall where the sun never directly hits. The result is a constant, gentle circulation of fresh air moving through your living space without any fan, any motor, or any utility bill. The system self-regulates. On hotter, sunnier days, the column heats more intensely and pulls more air. On cloudy days, the effect diminishes, but so does the need for cooling. The key numbers matter, and understanding them helps you build an effective system rather than a disappointing one. The black surface inside the column needs what engineers call an absorptivity coefficient of at least 0.9. That means it absorbs 90% of the solar energy hitting it and reflects only 10%. Regular flat black paint from a hardware store gets you there. Rust-Oleum, Krylon, and most generic brands of flat black spray paint or brush-on paint will achieve absorptivity ratings between 0.92 and 0.97. Glossy black paint, by contrast, might only reach 0.85 because the shiny surface reflects more light. Always use flat or matte finishes. The glass covering needs a transmission coefficient around 0.7, which is standard for most single-pane glass or polycarbonate panels. This means 70% of the sunlight hitting the glass passes through to heat the black surface inside. Double-pane glass actually reduces transmission slightly but improves heat retention, which can be beneficial in some designs. Standard quarter-inch tempered glass, the kind used in storm doors and picture windows, works excellently. Polycarbonate panels, often sold under brand names like Lexan or Suntough, are cheaper, lighter, and nearly unbreakable, though they scratch more easily and may yellow slightly after years of sun exposure. With those two materials and a clear southern exposure, researchers have measured effective heat capture exceeding 700 watts per square meter on a sunny day. To put that in perspective, a typical space heater runs at 1500 watts. A solar chimney with just 2 square meters of collection area, which is roughly a panel 4 feet wide and 5 feet tall, captures enough solar energy to match that heater. That is more than enough to drive serious airflow through a residential building. A family in Lancaster County showed me their records. They tracked indoor temperatures for 3 summers starting in 2014. On days when the outside hit 92 degrees, their main living area stayed between 74 and 77. No fans, no AC unit cycling on and off. Just that black column on the south wall doing what physics demands it must do. The father, a man named Eli, who works as a furniture maker, kept meticulous logs in a spiral notebook. He showed me entries from July 2015 when outdoor temperatures exceeded 90 degrees for 11 consecutive days. The highest indoor reading he recorded during that stretch was 78 degrees, and that was in the upstairs bedroom, furthest from the intake vent. But here is where the story takes a turn that most people never hear, and this is the part that made me realize I was not just learning about an alternative technology. I was uncovering something that had been actively suppressed. This technology is not new. It is not some obscure Amish invention that the rest of the world missed. Passive solar ventilation was studied extensively in the 1940s and early 1950s by agricultural researchers trying to help rural families live more comfortably without depending on expensive electrical infrastructure. These were land-grant universities funded by federal and state governments with explicit missions to improve the lives of ordinary Americans. The United States Department of Agriculture published multiple extension bulletins on passive cooling and heating systems between 1945 and 1953. Researchers at institutions including Cornell, Purdue, North Carolina State, and the University of California conducted field tests, published findings, and distributed practical construction guides. Then something happened. In 1951, the first affordable window air conditioning unit hit the American market. The Carrier Corporation, which had been manufacturing industrial and commercial cooling systems since Willis Carrier invented modern air conditioning in 1902, released its first mass-market residential unit in that year. General Electric followed within months. Fetters, Philco, and a dozen other manufacturers joined the rush. Within 3 years, sales of residential AC units went from a few thousand per year to over 1 million. By 1955, the industry was moving more than 2 million units annually. The companies making those units had enormous incentive to make sure every American family believed that mechanical cooling was the only real solution. I found a reference in an old extension report from the North Carolina Agricultural Experiment Station dated 1951. The document was titled Passive Ventilation Systems for Farm Structures and authored by a researcher named Harold B. Thompson, who had spent 6 years testing various solar-driven air movement systems at the university's experimental farm near Raleigh. It described exactly this type of solar-driven ventilation stack and noted that a properly sized column could reduce indoor temperatures by 12 to 18 degrees on summer afternoons compared to an unventilated structure of identical construction. The report recommended the technique for farmhouses and rural schools. It included construction diagrams with precise measurements. It listed material costs at under $100 for a full installation, which adjusted for inflation would be roughly $1,200 today, still far less than a central air conditioning system. That report was never updated. It was never digitized for modern databases. The funding for passive cooling research dried up almost completely by 1954, redirected to other priorities as rural electrification made mechanical cooling accessible to more families. Thompson himself left academia in 1956 to take a position with a heating equipment manufacturer. The report sits in a few university archives and has been cited exactly twice in the past 70 years, both times in obscure academic papers about the history of agricultural engineering. Meanwhile, the average American household now spends over $300 every summer running air conditioning. Some families in hot climates spend 3 times that amount. The industry that buried this knowledge has extracted trillions of dollars from families who were never told there was another way. Before I show you exactly how to build this for under $300, everything I have documented is in one place, the Amish home system. Link in the description, but stay here, because the corrugated metal technique I found buried in a 1951 archive is the part that changes everything. The Amish did not forget. They could not forget, because they never adopted the alternative. When you cannot plug in a compressor, you find ways that do not require one. And once you find a way that works, you pass it to your children, and they pass it to theirs. The knowledge stayed alive, not in universities or government publications, but in the lived practice of communities that had no choice but to remain self-reliant. Therefore, the question is not whether this technology works. The question is why you were never taught it existed. The question is who benefited from your ignorance and who continues to benefit every time you pay an electric bill to stay comfortable in your own home. The efficiency of a solar chimney depends on 3 factors: column height, temperature difference between the inside of the column and the outside air, and the size of your intake and exhaust vents. Taller columns create stronger draft because hot air has more vertical distance to accelerate as it rises. The relationship is not linear but follows the square root of height, meaning that doubling the column height increases airflow by about 40%, not 100%. Still, every additional foot of height helps. Hotter columns relative to ambient temperature create faster air movement. On a day when the outside air is 85 degrees and the interior of your solar column reaches 140 degrees, you have a 55-degree differential driving the system. That differential translates directly into air velocity. Engineers use formulas derived from the Bernoulli principle to calculate exact flow rates, but the practical takeaway is simple. More heat means more airflow, which is why solar chimneys work better on sunny days, precisely when you need cooling most. Properly sized vents ensure you get volume without losing velocity. If your intake and exhaust vents are too small, they restrict flow and the system underperforms despite adequate heat collection. If the vents are too large, the air moves through slowly and you lose the cooling sensation of perceptible airflow. The general guideline from the historical research suggests that vent cross-sectional area should equal approximately 1/50th of the floor area being cooled. For a 1,500 square foot house, that means intake and exhaust vents totaling about 30 square inches each, roughly equivalent to a rectangular opening 6 inches by 5 inches. For a typical single-story home with 8-foot ceilings, a solar chimney that extends 12 to 15 feet from the intake near the floor to the exhaust above the roof line will generate enough airflow to exchange the air in a 1,500 square foot house roughly once every 20 minutes. on a sunny summer day. That is better than most ceiling fans and competitive with low-setting central air in terms of comfort, though it works differently. You feel the air moving. The house breathes. There is a quality to the comfort that mechanical systems cannot replicate, a sense of connection to the environment rather than isolation from it. Two-story homes have an advantage. The natural height of the structure means you can build a taller column more easily, and the stack effect is amplified by the existing temperature stratification between floors. Hot air naturally accumulates on upper floors, and a solar chimney provides a pathway for that accumulated heat to escape. Some Amish families I visited had columns running the full height of a 2.5-story farmhouse with total vertical runs exceeding 25 feet. The airflow in those buildings was remarkable. You could feel a steady draft at ankle level in the basement that traveled all the way up through a central stairwell and exited through the solar chimney on the south gable. The entire house participated in the cooling, functioning as a unified thermal system rather than a collection of separately conditioned spaces. Now, if you already own a house and you are thinking this only applies to people building from scratch, stay with me, because this next part is specifically for you, and it addresses the most common objection I hear when I discuss this technology. You do not need to tear open your south wall to test this principle or even to implement a working version of it. There are two approaches that work for existing homes, and I have seen both done successfully by homeowners who had never built anything more complicated than a bookshelf. Neither approach requires specialized skills, expensive tools, or professional contractors. Both can be completed in a single weekend with basic hand tools and materials available at any hardware store or home center. The first approach is an exterior add-on column. You build a wooden or metal frame against your south-facing exterior wall. The frame holds a glass or polycarbonate panel on the outside and a black painted metal sheet on the inside. 2x4 lumber works fine for the frame, though some builders prefer aluminum angle brackets for lighter weight and better weather resistance. The spacing between the glass and the black surface should be between 3 and 6 inches, enough room for air to flow freely, but not so much that the volume of air becomes difficult to heat. The bottom of this column connects to a vent that you cut through your exterior wall into a low point in your house, ideally a basement or crawl space. The top of the column vents to the outside air above your roofline. Extending above the roofline matters because you want the exhaust point in a zone of lower pressure where wind effects can actually enhance the draft rather than fighting against it. When the sun heats the black surface, the column draws air from inside your house and exhausts it outside. You then need a corresponding intake vent on the north side of your house, positioned low, to allow fresh air to enter and replace what the column is pulling out. The materials for this kind of add-on column cost between $150 and $300 depending on your local prices and whether you can source any components secondhand. A standard 4x8 sheet of polycarbonate runs about $40. A similar sized piece of sheet metal costs $15 to $25. Lumber, fasteners, sealant, and paint make up the rest. The construction takes a weekend if you work alone, less if you have help. The only permanent modification to your home is 2 vents, each roughly the size of a dryer exhaust. If you ever decide to remove the system, patching those holes takes less than an hour. I met a retired electrician named Douglas Harmon in rural Virginia who built one of these in 2019 after his wife showed him a magazine article about passive cooling. He told me his summer electric bill dropped by nearly 40% the first year, from an average of $220 monthly to $135. He was running his central air only at night, letting the solar chimney handle the afternoon and evening hours when electricity rates in his area peak. The system paid for itself in a single season. When I spoke with him again in 2022, he had built a second column on the opposite end of his house and reported that he barely used the central air at all, except during the most extreme heat waves. The second approach is even simpler and requires no permanent modification at all. You build a freestanding solar chimney as a box structure and position it against a south-facing window. The intake side of the box connects to the window opening. The box itself is tall, painted black inside, and covered with glass or clear plastic on the sun-facing side. When sunlight heats the interior of the box, air rises and exits through a vent at the top, pulling air from inside your house through the window. This version is not as powerful as a built-in or attached column because the vertical height is limited by practical considerations, usually no more than 6 or 8 feet. But it works, and it costs almost nothing to build. I have seen versions made entirely from materials salvaged from old storm doors and scrap lumber. One man in Pennsylvania named Robert Ziegler built his from 2 discarded sliding glass door panels he found at a construction site dumpster and a few 2x4s left over from a deck project. His total cost was under $50, including the black spray paint and a tube of silicone caulk for sealing the joints. He used it to supplement his basement cooling and said it made a noticeable difference on sunny afternoons, dropping the basement temperature by 6 to 8 degrees compared to days when he left the window closed. The critical factor with any of these systems is ensuring you have a corresponding intake path for cool air. The chimney only works if air can flow into the house to replace what it pulls out. Without that intake, you just create a partial vacuum and the airflow stalls. The negative pressure will pull against closed windows and doors rather than moving air through the living space. Position your intake vent on the north or east side of your home, as low as possible, ideally in a shaded area where the air temperature stays several degrees cooler than the sunny side of the building. Some families run their intake through a buried pipe that passes underground for 20 or 30 feet before entering the basement. The earth below the frost line maintains a fairly constant temperature year-round, typically between 50 and 57 degrees depending on your geographic location. Air traveling through a buried pipe picks up that coolness before it ever reaches the living space. This combination of a solar chimney on the south and a ground-cooled intake on the north creates a system that outperforms many mechanical AC units on all but the hottest, most humid days. One family I visited in eastern Ohio had a 100-foot intake pipe buried 4 feet deep, running from a shaded inlet near their wood line to the basement. The air coming out of that pipe on a 90-degree day measured 62 degrees. Combined with their solar chimney, their house stayed comfortable through every summer day I asked about. But there is another side to this technology that almost no one discusses. What happens in winter? This question stopped me when I first started researching solar chimneys, and the answer transformed my understanding of what these systems can actually accomplish. The same column that cools your house in summer can heat it when the days get short and cold. The principle is identical. Sunlight heats the black surface inside the column, hot air rises. But in winter, you do not want that air escaping outside. You want it flowing into your living space, bringing that captured solar energy with it. The solution is a simple damper system, mechanical flaps that redirect airflow depending on the season. At the top of your solar chimney, instead of a fixed exterior vent, you install a damper that can be closed. At the bottom of the column, where it connects to your interior, you install a second vent that opens directly into the house rather than pulling air from inside. In summer mode, the top damper is open and the bottom interior vent is closed. Hot air exhausts outside, creating the negative pressure that pulls cool air through your home. The column functions as a thermal exhaust system. In winter mode, you reverse it. The top damper closes, the bottom interior vent opens. Now the heated air inside the column has nowhere to go but into your living space. The column becomes a passive solar heater. On sunny winter days, even when the outside temperature is in the 30s, the air inside that black column can reach 120 degrees or higher. I have personally measured temperatures exceeding 140 degrees inside a solar column on a clear